Welcome to the deep dive. Today we're plunging into a really fascinating mix of things. We've got textile science, some cutting-edge digital fabrication.
Mm,
The whole world of biomaterials are super interesting, and wearable technology.
yeah, a lot going on there.
Exactly. So our mission really is to pull out the key insights for you from this collection of research and experiments.
Yeah.
A lot of it seems linked to the Fabricademy program.
That's right. And what's really cool is seeing how these fields, which might seem separate, actually, well, they weave together.
Interconnected. That's the
They-
word I was looking for.
Totally. The sources we have really show how, an idea from one area can totally spark something new in another. You see these surprising links.
And hopefully we can highlight some of those aha moments for you listening. We've got a lot of material here, web pages, experiments,
Yep, quite a bit.
and we know everyone listening has different technical backgrounds, right? So the aim isn't to get bogged down in jargon.
No, definitely not. More about the core ideas, the interesting takeaways.
Okay, great. So let's dive in. First up, textile scaffolds. What are these fundamentally, and why are they so important in these fields we're looking at?
Okay, so textile scaffolds, think of them as adaptable frameworks, usually flexible, often lightweight, made from all sorts of materials.
Frameworks, okay.
Yeah, and their importance really comes down to versatility. They provide this foundation, this underlying structure for both biomaterials and wearables.
So like in biofabrication, you mentioned that.
Exactly. In biofabrication, they can be engineered to sort of mimic the natural environment around cells. It's called the extracellular matrix, or ECM.
Ah, the ECM, right. The stuff that supports cells in tissues. So these scaffolds act like a temporary support, helping cells grow into new tissue.
You got it. They guide that biological growth, like a blueprint almost.
Okay, guiding growth. So what makes a good scaffold then? Can't just be any structure, right?
Definitely not. Key properties are crucial, like biocompatibility. That means it won't harm the body.
Makes sense.
And porosity, that's really important. It needs tiny holes so nutrients can get in and waste can get out.
Right, for the cells to live.
Precisely. And then there's flexibility, stretchability.
Hmm.
Especially for wearables, you need that scaffold to move with you comfortably.
Yeah, you wouldn't want a stiff patch sewn onto your shirt. Okay, so biocompatible, porous, flexible.
Yeah.
Got it. Now, one source made this really interesting comparison. Nabat sugar crystallization. How does that relate?
Ah, yeah, that was a cool connection. It's about the principle of controlled formation. Nabat is this traditional Iranian sugar, right? That forms these amazing geometric crystals, often on a thread.
Look. Mhm.
And how those crystals grow depends entirely on the conditions, like how much sugar is dissolved, the saturation, the temperature, how long you leave it.
So managing the environment to get a specific structure.
Exactly. Just like designing a textile scaffold for a specific biological or tech purpose, you're controlling the process to get the outcome you want.
That's a neat parallel.
Yeah.
So the Nabat process itself,
Yeah.
how does that work?
Well, the details mentioned were things like picking the right solvent, dissolving the sugar until the water can't hold anymore, filtering out impurities,
Uh-huh.
then cooling it really slowly. Sometimes they add a tiny seed crystal to kick things off.
Okay.
And things like purity, keeping the temperature super stable, not disturbing it, maybe even making it super saturated. They all affect the final crystals. It really shows how this delicate balance creates complex structures.
Wow. From sugar to cells.
Yeah.
The same basic ideas apply.
Yeah.
That's pretty cool. Okay, let's shift gears. Molding experiments. The sources talked about leather molding first.
Mm-hmm.
What were the main steps there?
Right, the leather molding, specifically using fruit leather, it was quite meticulous. First, preparing the mold itself, usually wood. Checking it, maybe sealing it, cleaning it really well.
Important prep work.
Crucial. And then moisturizing the mold surface slightly so the leather doesn't stick or, crack later.
Ah, okay. Mold prep is key. Then the fruit leather.
Yeah, you need the fruit leather itself. It has to be thin, flexible. They mentioned lightly spraying it with water to make it more pliable, easier to shape into the mold.
Soften it up a bit.
Exactly. Then you monitor the drying. Got to make sure it dries evenly, doesn't warp. And finally, carefully demolding it once it's totally dry.
And they took it a step further, right? Adding lace fabric.
Yeah, that was interesting. They embedded lace into the fruit leather during molding.
What'd that do?
Two things, really. Aesthetically, it added these cool, intricate patterns. But structurally, and this links back to our scaffolds idea, the lace acted as reinforcement, made the fruit leather stronger.
Oh, nice. So function and form. combining materials for better results.
Exactly. It's a great example of that cross-pollination.
Definitely. The experiments also looked at the molds themselves. Moisture absorption, soft versus hard molds.
Yeah.
What did they find out there?
That was quite practical stuff. They found moisture-absorbing molds, like wood or plaster maybe, can be good for materials that need slow, even drying. They help pull moisture away. But for non-absorbent molds, say plastic, sometimes you might embed absorbent stuff in the mold to manage evaporation, especially for things like air-dry resins.
Interesting. And the soft versus hard mold combinations.
Yeah, that matters too. Soft molds, like silicone, are often great for casting rigid materials because the mold can flex to release the object.
Right, easier to pop out.
Yep. And hard molds give firm support, which is better for shaping soft materials while they set or dry. They also found optimizing the mold design, like adding little channels for moisture to escape, really helps drying efficiency.
Really practical tips for anyone doing molding. Okay, then they moved into CNC machining, starting with a wax mold.
That's right. CNC machining a wax mold is quite a process. Starts with software designing the 3D shape, planning the tool paths.
Tool paths.
Yeah, the route the cutting tool takes. You select the right tools, like flat or ball-end mills, set speeds, and feeds how fast the tool spins and moves.
Okay.
Then you run a simulation, super important, lets you see if it'll work, catch errors before you cut. Then you generate the G-code. That's the actual language the CNC machine understands. Tells it exactly where to move, how fast, etc.
Like instructions.
Precisely. Set up the machine, clamp the wax block down, and run the job, watching carefully.
And they mentioned something about wax being regenerative?
Yes, this was a key insight. They had a cutting error, but instead of junking the whole block, they could just melt more wax, fill the mistake, and remachine it.
That's brilliant. So much less waste.
Totally. It shows how material choice impacts sustainability in prototyping. Wax is forgiving.
Great point. Okay, what about the epoxy resin molding? Sounds like that didn't go as smoothly.
No, that hit some snags. The mold they designed wasn't great for epoxy. Main problem. No way for air to escape easily.
So bubbles trapped inside.
Worse, actually. It led to uneven drying. The outside hardened, but the inside stayed gooey, uncured.
Oh, okay. Not good.
And the mold itself was rigid, and epoxy cures rigid. So trying to get the cast out damaged both the piece and the mold.
Ouch. So takeaway.
Really highlighted the need to match the mold properties to the material being cast. That same mold, though, worked fine for soap. Different properties.
Right. Matching molded material. Makes sense. And the soap molding was simpler.
Much simpler, yeah. Use silicone molds, which are flexible. Just melt the soap base, add color or scent, pour it in, tap out bubbles.
Let it cool.
Let it cool and harden, then just pop it out of the flexible mold. Easy peasy.
Silicone for the win there. Okay, safety. CNC machines are serious business. The research detailed safety precautions. What were the highlights?
Absolutely critical. They broke it down really well. For the operator, stay focused. No gloves or loose clothes. Get proper training. Keep hands clear when it's running.
Standard machine safety, yeah.
Right. For the space.
Yeah.
Keep it clear. Stay a safe distance. Know where the emergency stop is and make sure it's accessible. Good ventilation.
E-stop. Always know where the e-stop is.
Always. For the machine.
Oh.
Keep guards closed, tools tight, do maintenance, be aware of high voltage, use the e-stop during setup too. And finally, material setup. Clamp it securely, clear the path, use the right material, correct speeds and feeds, double check for collisions. It's a lot, but essential.
Definitely sounds comprehensive. Good reminder.
Yeah.
Okay, let's shift now. 3D printing in fashion and textiles. Big area. What are the main advantages here?
Huge advantages. 3D printing offers, well, incredible design freedom. You can create really complex, customized shapes that are hard or impossible otherwise.
Customization, yeah.
Big time. And material efficiency. You only add material where you need it, unlike cutting away from a block. Less waste.
Additive versus subtractive, right?
Exactly. Plus, it's great for limited editions or rapid prototyping. You can iterate designs much faster. Big plus for fashion.
And they mentioned printing directly onto fabric. How does that work?
Yeah, direct fabric integration, basically printing right onto a textile surface. This lets you embed rigid or decorative bits seamlessly into fabric.
Oh.
Creates these flexible, wearable items. Machines like the Stratasys J850 were mentioned. They can print different materials, rigid and flexible, in one go. Think about embedding functional parts right onto those textile scaffolds we talked about earlier.
Wow, okay. So combining the structure of the fabric with printed elements.
Yeah.
Very versatile. Now, the research included a table of other textile fabrication methods too, not just 3D printing. Why include that?
Good question. It provides context. Understanding traditional methods like spinning, knitting, weaving, even things like electrospinning, it shows where 3D printing fits in.
So it's not replacing everything.
Not at all. It's another tool. The table outlined how each process works, the materials, the applications. It highlights the strengths and weaknesses of each, positioning 3D printing as this new complementary technique.
Got it. Another tool in the toolbox. Fascinatingly, they even sketched out a concept for a 3D printer specifically for biomaterials, like alginate or gelatin.
Yeah, a dedicated bioprinter concept. The main idea was building something optimized for these often quite viscous, sustainable materials.
So what were the key design thoughts?
Precision movement was paramount. X, Y, and Z axes needed to be super accurate for layering these materials correctly.
Makes sense.
For X and Y, the horizontal movement, they envisioned a linear rail system, stepper motors, belts pretty standard for speed and smoothness.
Okay.
But for the Z-axis, the vertical layering, especially with delicate biogels, they opted for a geared movement, like a gear and lead screw system, offers more precise control and stability.
Slower but more accurate for the vertical build.
Yeah.
Smart. What other features did this conceptual printer have?
Well, biomaterial compatibility was huge. Thinking about nozzle designs for thick gels, maybe needing heating or cooling.
Like different materials need different conditions.
Exactly. And adjustable precision, balancing the speed of belts for X, Y with the resolution of gears for Z. Plus, a real focus on being eco-friendly. Using biodegradable materials, designing it modularly so you could upgrade or repair parts easily, extending its life.
A sustainable printer for sustainable materials.
Right.
Makes sense. What about the actual build? Materials for the frame, the extruder.
For the prototype frame, they suggested aluminum extrusion profiles. Lightweight, strong, easy to assemble with standard brackets and connectors. Very modular.
Like a high-tech erector set.
Kind of, yeah. And for the extruder and other supporting parts, gear housings, motor mounts, they proposed 3D printing them using PLA filament.
PLA.
Yeah, common 3D printing plastic. Easy to print, strong enough for those parts. The process would be CAD model it, print it on a standard FDM printer.
Fused deposition modeling, the common plastic melting tech.
Right. Then clean up the print, remove supports, smooth it, and integrate it into the aluminum frame, building the machine using the technology itself in a way.
Very meta. Okay, let's jump to another cutting-edge topic. Skin electronics, what are these?
Skin electronics are basically ultra-thin, flexible electronic devices designed to conform to the body, almost like a second skin.
Wow, like electronic tattoos.
Sort of, yeah. Their potential is huge because they can monitor health or interact with us non-invasively, continuously. Very different from rigid gadgets. Think health tracking, interfaces, even aesthetics.
Sounds amazing.
Yeah.
What are the key research areas driving this?
Material science is massive. Finding stretchable, biocompatible conductive polymers, graphene, liquid metals.
Okay.
Developing tiny flexible sensors and actuators to measure things and provide feedback. Figuring out power flexible batteries, maybe harvesting energy from body heat or movement.
Energy harvesting, cool.
Yeah. And integrating tiny processors, wireless communication. The applications in medicine are especially exciting. Glucose monitoring, drug delivery patches.
And it can't be easy, right?
Yeah.
What are the hurdles?
Definitely challenges. A big one is balancing durability with that essential flexibility. Making them stick reliably to skin long-term without irritation is another.
Yeah, adhesion is tricky.
And then scaling up manufacturing, making these complex, tiny things affordably and in large numbers, that's still a work in progress.
Makes sense. The research mentioned a specific idea, monitoring body swelling automatically. How would that work?
That was a neat concept. Imagine sensors may be resistive, capacitive, or stretch sensors placed on areas prone to swelling, like limbs after surgery.
Okay.
These sensors detect changes in volume or skin tension. A small processor analyzes the data, sends it wirelessly to, say, a nurse's station. An alert unit there could trigger a light or sound showing where and how severe the swelling is, powered by tiny batteries, maybe rechargeable or energy harvesting.
So faster detection, less manual checking.
Exactly. Could catch problems early, prevent complications, and free up nursing time. A really proactive system.
Very clever. Okay, different direction now. Circular open source fashion. What's the core idea there?
Circular fashion is all about designing waste out of the system, moving away from that take, make, dispose linear model.
The usual way.
Instead, it focuses on keeping clothes and materials in use longer through repair, reuse, eventually recycling, and ideally regenerating natural systems at the end of life.
A closed loop.
That's the goal, making fashion sustainable from the start.
And the term itself is relatively new.
Yeah, coined by Dr. Anna Brismar of Green Strategy back in 2014. She defined it as designing, making, and circulating fashion items responsibly, keeping them valuable as long as possible, then returning them safely to the environment.
Got it. Now, the research used an ancient Persian symbol, the Faravahar, as inspiration. How did that translate into design?
The Faravahar, yeah. Big symbol in Zoroastrianism, seen in places like Persepolis, represents divine spirit, balance, progress.
Okay.
The researcher was inspired by its feathered wings, seeing them as representing modular construction, individual parts creating a whole.
Ah, like feathers making up a wing.
Exactly. So the design used interlocking modules, creating this flexible, scalable system, like the wings giving balance and flight to the symbol.
Taking ancient symbolism for a modern design principle. Cool. How do they actually create this modular design from sketch to fabric?
It was a mix of hand and digital. Started with sketching the wing idea, focusing on symmetry, identifying modules, then hand-cutting paper versions to see how they fit.
Physical prototyping.
Yep. Then scanned the paper design, vectorized it in Corel Draw, turning shapes into editable curves, set hairline widths for the laser cutter, checked dimensions, saved it as a DXF file, which laser cutters use, then nested the modules efficiently in the software, arranging them to waste minimal material. Even manually tweaked lines to avoid double cuts.
Not nesting.
Essential for efficiency. Laser cut a paper test model first, then move to textiles felt, synthetics, denim, canvas testing, and adjusting laser settings for each fabric.
Different fabrics need different settings.
For sure. And finally, manually assembled the cut textile modules, bringing the whole concept together.
Quite a journey from symbol to garment. The research also talked about cutting direction in fabric. Why does it matter if you cut along the grain or on the bias?
Huge difference. Cutting along the grain, following the warp and weft threads, gives you less stretch, more stability, easier to sew, holds its shape. Good for structured clothes.
Okay, the standard way for many things.
Right. But cutting not along the grain, especially on the bias that's a 45-degree angle, introduces a lot more stretch and flexibility, even in non-stretch fabrics.
The bias cut, right, known for drape.
Exactly. Gives you better drape, a fluid fit that follows the body's curves. More elegant look, but it can distort more easily, needs careful handling, so it affects durability and aesthetics. Structure versus flow.
A deliberate design choice.
Yeah.
Okay, moving on to biochromes. Sustainable dyeing. What are these?
Biochromes are basically natural dyes and pigments from plants, algae, fungi, bacteria, biological sources. They're getting attention as a sustainable alternative to synthetic dyes.
Because synthetic dyes can be pretty bad for the environment.
Yeah, often use harsh chemicals, lots of water, non-renewable resources. Biochromes aim to minimize waste, use less water, rely on renewable stuff.
Makes sense. But natural dyeing isn't new. What are the modern challenges or research focuses?
True, it's ancient, but modern challenges include consistency. Getting the same color shade every time can be tricky with natural sources.
Oh, variability.
Exactly. Scalability is another big one. Making these dyes work efficiently on an industrial scale. And color fastness, making sure the color doesn't fade too quickly. Research looks into natural mordants, fixatives, to improve that.
Okay.
Plus, identifying new, stable, sustainable sources, both traditional plants and maybe even bioengineered microbes that produce pigments?
Bioengineered microbes. Wow. The research mentions some inspiring examples.
Definitely. Nienke Hoogvliet's Living Color Project uses algae pigments for biodegradable, non-toxic colors.
Algae, interesting.
And Roya Agayi's biogarmentry created an algae biofabric that actually photosynthesizes, purifying air while being naturally colored. Super innovative stuff.
That's incredible. Living textiles. Okay, the research got practical too, with dye recipes. Let's talk cochineal. What's the process? What color do you get?
Cochineal comes from crushed bugs, actually. Gives you reds to pinks. The process involves pre-treating the fabric with a mordant, like alum, then dissolve the ground cochineal in hot water, add the fabric, and gently simmer.
Simmering bugs.
Yeah. And you can tweak the pH, add vinegar for brighter pinks, a mild alkali for more purple tones. It's quite hands-on.
Definitely sounds complex.
Uh-huh.
What about helichrysum or saffron? What colors do they give?
Helichrysum flowers yield golden yellows to light oranges. Similar process. Simmer the flowers to get the dye, then simmer the mordanted fabric in it. Citric acid or vinegar can adjust the shade.
Okay.
Saffron, just the threads, gives yellow to golden hues. Soak the threads, simmer, then dye the fabric. The amount of saffron really dictates the intensity. Very precious, obviously.
Right. Expensive spice, expensive dye. They also experimented with different mordants for saffron on canvas. What worked best?
Yeah, they tried 6 combinations: vinegar plus alum, alum alone, soda, vinegar alone, fabric softener, interesting, and soda plus alum together.
And the winner was.
The combination of alum and soda used together gave the best results, most vibrant and uniform color. Vinegar alone was okay too, but less even. Shows how crucial the mordant choice is.
Big impact. And staying with the circular theme, they talked about recycling dye from wastewater. How do you do that?
Yeah, extracting leftover pigment from the dye bath water, general idea. Filter the water first.
Mm-hmm.
Then adjust the pH to make the dye molecules basically fall out of the solution precipitate.
Into the chemistry.
Right. For most natural dyes, making it more acidic with vinegar or citric acid works. Sometimes ethanol is involved earlier. Once the pigment settles, you filter it out, maybe dry it further.
And can you reuse that pigment?
That's the idea. Specific recipes were mentioned for extracting pigment from cochineal water using acid, indigo water using alkali like soda ash for blue, and saffron water using acid again. Potential for reuse as dye or maybe natural inks.
Closing the loop again. Cool. Okay, quick mention of e-textiles. An example with LEDs blinking together. What effect did that create?
The simultaneous blinking, it just creates this strong sense of unity, synchronization, like a pulse. Good for emphasizing a uniform state or just grabbing attention.
Simple but effective. Now, computational couture. Merging digital tech with fashion. What does that involve?
It's a really exciting field. Uses digital tools for fashion creation. Think 3D printing for unique shapes, parametric design,
Parametric.
designing with rules and relationships so designs can adapt easily. Also generative design, where algorithms help create complex patterns, laser cutting, CNC milling for fabric details, and integrating wearable tech, of course.
Lots of tech involved. Neri Oxman was mentioned again here.
Yes, her work in biodesign is hugely influential, merging design, biology, digital fabrication. Her silk pavilion, woven by silkworms, guided by algorithms, is iconic. Pushes boundaries in materials and process.
Inspiring stuff. To get practical, the research detailed getting familiar with 3D printing. Mentioned a table comparing FDM, SLA, SLS printers. Key differences.
Right, that table gave a good overview. FDM is the common filament melting type, often larger build volume, uses PLA, ABS, good for prototypes.
Well, workhorse.
Kinda, yeah. SLA uses a laser on liquid resin. Higher resolution, great for detailed models.
Resin printers, okay.
And SLS uses a laser to fuse powder, usually nylon. Creates strong, functional parts, often used in industry. The table compared things like layer thickness, speeds, materials, software.
Yeah.
Gives you a sense of the trade-offs.
Good comparison, but you need to talk to the printer. G-code and slicer software, like Cura, what do they do?
G-code is the printer's instruction language. Tells it exactly where to move, how hot to get, when to extrude material. Every line is a command.
The recipe for the print.
Pretty much. And Cura, the slicer software, takes your 3D model and cuts it into super thin horizontal layers. It figures out the nozzle path for each layer and generates that G-code based on your settings, speed, temperature, etc.
It translates the model into instructions.
Exactly. Digital design to physical object via G-code.
The research walked through printing in PLA and TPU. Any major differences in settings or process for those?
The basic workflow was similar. Prep the file, slice it with specific settings, load filament, level the bed, print, post-process.
Standard steps.
Yeah, but the settings were different. PLA, the rigid plastic, used lower temps, maybe 210 degrees C nozzle, 50 degrees C bed, printed faster, like 100 millimeters.
Okay.
TPU, the flexible stuff, needed higher temps, 240 degrees C nozzle, 55 degrees C bed, and printed much slower, maybe 30 millimeters for good quality and adhesion. Material properties dictate the setting.
Slower for flexible materials.
Yeah.
I like it. They also tried printing directly on lace. What were the challenges there?
Yeah, tricky stuff. Lace is uneven, right? Hard to level the print bed perfectly on top of it. That's crucial.
Bed leveling is always key.
Always. Plus, the delicate lace texture could snag on the nozzle, and the heat from the nozzle made the polyester lace tense up and soften. Not ideal. They suggested maybe using special adhesives to stabilize the fabric first.
Creative problem solving needed. And finally, on 3D printing, recyclability. What's the situation with common materials?
It varies. PA and ABS are sometimes recyclable in standard systems. PLA, though plant-based, usually needs industrial composting, not typical recycling.
So PLA isn't easily recycled curbside.
Generally not. And TPU, nylon, resins, mostly not widely recyclable, often need specialized facilities, if any. So end of life is a big consideration when choosing materials.
Definitely something to think about for sustainability. Okay, let's shift to biofabricating materials. Creating stuff from biology. What's the big picture?
It's about harnessing biology for sustainable materials. Two main types,
Oh.
grown and crafted.
Grown versus crafted.
Yeah, grown means cultivating organisms, like growing mycelium mushroom roots into materials, or using the bacteria in kombucha to make bacterial cellulose sheets.
Okay, living factories.
Sort of.
Okay.
Crafted is more like mixing biological ingredients, gelatin, alginate, agar, maybe with a plasticizer like glycerin, then molding or spreading them and letting them dry or cure, like making fruit leather or bioplastics.
And some pioneers were mentioned.
Suzanne Lee, founder of BioCouture, is huge in bacterial cellulose. Neri Oxman, again, with her broad biodesign work. And companies like MycoWorks are commercializing mycelium leather.
Bringing it to market.
Oh.
Okay, the research went deep into recipes. Biosilicone from gelatin. What were its properties?
Right, gelatin, water, glycerin. It shrank a fair bit, maybe 25%, that held its shape. Very flexible, rubbery, like silicone. Smooth surface, not too sticky.
Uh-huh.
Reasonably transparent, pretty strong, resisted tearing, could stretch, took days to dry fully, held color well, but interestingly, didn't biodegrade easily, decompose slowly.
Slow decomposition. How did gelatin foil, similar recipe, compare?
Similar ingredients, but made as a thin film. Shrank less, maybe 20%, but edges curled if not dried flat. Flexible when fresh, but got harder over time.
Became more brittle.
A bit, yeah. Smooth, slightly shiny surface, bit sticky at first, not as strong as the thicker biosilicone, more sensitive to moisture too. Dried faster, maybe a day or two. Held pastel colors but faded in UV light, and this one was noted as biodegradable.
So thickness and drying really changed things. What about alginate or agar foils?
Alginate foil from seaweed extract uses calcium chloride to set, was smooth, flexible, somewhat stretchy, translucent, durable, but sensitive to humidity. Agar foil, also seaweed-based with glycerin, started flexible, got firmer, bit brittle at edges, smooth, shiny, translucent, moisture-sensitive but stable when dry, broke down quickly in compost.
Different properties again. And fruit leather.
Mm-hmm.
Beyond being tasty, how is it a biomaterial?
Well, the process pureeing fruit, drying it thin, is a natural form of creating a polymer film. The result is durable, flexible, like a natural leather substitute.
Huh. Never thought of it that way.
Right, and it's edible, food safe, naturally colored, inspires ideas for safe packaging or materials. It's looking at traditional things through a biomaterial lens. Traditional Persian labashak and Armenian tulavash were mentioned as examples.
Cool perspective. The research compared lots of these bioplastic experiments. What was the main conclusion from trying all these recipes?
A big takeaway was that early problems were learning opportunities. They improved recipes over time, and drying speed was critical.
How so?
Fast drying could cause unevenness, cracking, warping. Slower, controlled drying led to more uniform materials, potentially affecting density, flexibility, overall properties. Patience pays off.
Got it. And kombucha, how does that fit into biofabrication?
Kombucha fermentation produces bacterial cellulose, that rubbery disc, the SQOBY, grows a layer of it. You can harvest that layer, rinse it, maybe boil it, stretch it, dry it, and you get kombucha leather.
Wow. Properties, limitations.
It's flexible, biodegradable, customizable texture-wise. Big limitation is water sensitivity. It can get weak or slimy if wet, though treatments like waxing help. Keeping the pH right during fermentation is also key for the bacteria to work well.
Fascinating.
Sure.
Okay, next up, soft robotics. How are these different from regular robots?
Big difference is materials. Soft robotics uses flexible stuff, silicone, gels, polymers, not rigid metal and plastic.
So
Exactly, which makes them inherently flexible, adaptable. They can bend, stretch, conform to shapes, handle delicate things safely, often lightweight, safer for human interaction. Think octopus arms, not factory robot arms.
the biomimicry, right? Inspired by nature.
Very much so. Designs often mimic worms, jellyfish, tentacles to get that fluid movement.
Who are the key people in this field mentioned?
Neri Oxman, again, her material ecology work touches on it. Banaz Farahi explores soft robotics in interactive wearables. Cecilia Lasci is a major pioneer, especially in marine-inspired soft robots for underwater use. Shows the overlap between fields again.
Definitely. And the researcher had a fun connection to party horns.
Ah, yeah. The simple party blower unrolls when you blow, rolls back up. That's basic soft actuation. Uses air pressure and material elasticity, a simple everyday example of the core principle.
Love that. Okay, experiments with silicone. Using pre-made molds and 3D printed ones. What do they do?
With pre-made molds, they mixed two silicone types, Epoxy Master 5A, sturdier, and Silicone 0A, more elastic. Poured them, let them cure, demolded, then tested by inflating with air to see how they moved, how well they sprang back.
Comparing the materials.
Right. With 3D printed molds, they designed molds with internal air channels. Printed the mold, poured silicone, sealed it, cured it, demolded, made an air inlet, then tested inflation, deflation again. A video showed the process too.
Hands-on testing. What factors really affect how these silicone robots behave?
Material properties are key. The silicone's stretchiness and springiness, viscoelasticity, tear strength, hardness, even heat conductivity.
Okay.
Then geometry. The robot's shape, size, wall thickness, how the moving parts actuators are designed, and finally, the manufacturing process itself can influence performance.
Lots to consider. The research included a detailed table on silicone characteristics, advantages, limitations.
Advantages were many. Soft texture, flexible, easy to mix, durable against abrasion, transparent options, low viscosity for detail, safe once cured, good temperature range, fast curing possible, weather resistant.
Sounds great. Downsides.
Limitations included, maybe not rigid enough for structure, lower impact resistance, careful mixing needed, not for extreme heat or abrasion, needs pigments for color, can trap bubbles, uncured state can be irritating, limited UV chemical resistance, needs controlled cure temp, compatibility needed for additives. It's a balance.
Good summary. Okay, wearables again. What specific research areas were explored here?
Several things. Thermochromics, color-changing materials responding to heat. Wearable actuators, vibration motors, heat pads, LEDs looking at power use integration, soft circuitry conductive threads, fabric circuits connecting hard electronics to soft textiles, microcontrollers like Atiny, Arduino, Adafruit Flora programming, power, I/O capabilities, and body sensors, temp, humidity, heart rate as input.
Covering a lot of ground. The floorboard project started as a sunscreen reminder. What did it become?
Yeah, the UV sensor wasn't available, so they adapted it. Became a light sensor and buzzer project, still environmental monitoring and alert, but using ambient light level instead of UV.
Okay, components.
Flora board, a light sensor, LDR, a buzzer for sound, jumper wires, and a battery pack. Connect the sensor and buzzer to the Flora, program it to buzz based on light level.
Simple but effective. What about the reflective sensor experiment with an LED and LDR? How does that work?
Basic setup. LED shines light out, LDR nearby waits to detect reflected light. Object comes close, reflects light onto the LDR, LDR resistance changes.
Detects presence.
Yep. Good for obstacle detection, touchless switches, simple proximity sensing. Code examples were provided for Arduino reading the LDR.
Handy little circuit.
Yeah.
Then integrating a sound sensor and neopixels.
Connected a sound sensor and those colorful neopixel LEDs to the Flora. Wrote code to map sound level to color. Quiet might be blue, medium green, loud red, for example. Visualizing sound intensity.
Tool visualization. The LED experiment seemed to evolve quite a bit.
Yeah, it was a real progression. Started with just blinking one LED, then staggered blinking for chasing effects, then synchronized choreography inspired by the movie Interstellar, timing blinks to music, even using AI for coding help.
Wow, from simple blink to AI-assisted choreography.
Right. Then an audio equalizer idea using neopixels to show different sound frequencies. And finally, just a simple digital sound trigger, blue for sound, red for silence, shows learning and building complexity.
Great example of iterative exploration. Soldering a XIO RP2040 board, what was involved?
That required precision. The XIO is tiny. Had to carefully align its pins to the pads on the main board, then solder each pin individually, making sure no solder bridged between pins, shorts.
Delicate work.
Very. Check connections, clean up excess solder, and flux. Needed a steady hand.
I bet. Lastly, for wearables, displaying time with sound, inspired by a fancy watch.
Yeah, the Bulgari Octo Finissimo Ultra COSC. The idea was auditory time telling. Use the Flora board, Fabricademy, and a buzzer.
How did it represent time?
Single beeps for the hour, double beeps for each quarter hour, 15, 30, 45 minutes. A longer beep every 15 seconds. Code used the millis, function for simulated time, generated the different beep types, adjustable speed and tones.
Create a translation of time display. Okay, let's talk challenges. The magnetic textile project. What was the goal and what went wrong?
Goal was ambitious. Turn a super paramagnetic material, magnetic only when a field is applied, into a hard magnet. Retains magnetism.
Okay, permanent magnet textile.
Right. They synthesized a super paramagnetic textile using iron and nickel nitrates. But making it hard magnetic needed a really strong magnetic field, like 1 Tesla, which they didn't have access to.
Equipment limitation.
Yeah. Plus, experiments trying to incorporate cobalt, another magnetic element, were unstable, even caused an unexpected small explosion once. Safety issue. So despite efforts, it stayed soft magnetic.
Sounds tough. Future strategies.
Find access to a high-field magnet source. Explore different synthesis methods for cobalt stability, like hydrothermal or sol-gel, and maybe post-synthesis heat treatment, annealing, to improve magnetic structure.
Keep trying different angles. Okay, shifting from high-tech to traditional craft. Palm fiber weaving, Boria.
Yes, a commitment to reviving indigenous sustainable arts. They made a cat shelter using palm fiber thread and bordia weaving, which is ancient mat weaving,
Boria weaving.
believed to be older than textile weaving. Evidence from Iraq back to 5000 BCE and various ancient sites in Iran, traditionally used for floor mats, roofing, walls.
Wow, ancient craft.
So the cat shelter was a modern tribute using sustainable local materials connecting to that deep history.
Lovely connection. And finally, natural fiber reinforced composites. What was the research there?
Focused on improving Cordenca fibers, a type of regenerated cellulose, using 3D printing tech from 3D systems to develop prototypes, basically merging chemistry and fabrication to explore new possibilities for these natural fiber composites in textiles.
Pushing the boundaries of materials again.
Oh,
Okay, we've covered an incredible amount of ground here, from scaffolds to soft robots, ancient weaving to computational couture. What connections or aha moments really stick out?
the interconnectedness, definitely. Seeing how sugar crystal principles inform scaffold design, how lace reinforces fruit leather, how a party horn illustrates robotics, it's all linked.
Yeah, those unexpected links are fascinating.
And the constant theme of blending traditional knowledge or natural processes with cutting-edge tech. Fruit leather as a biomaterial model, ancient weaving from modern objects, drawing inspiration from nature for robots and dyes.
Absolutely. It points towards this future where tech, sustainability, and even biology are deeply intertwined, not just using resources, but creating with them thoughtfully.
Exactly. This whole deep dive into personalized, bio-integrated, sustainable tech, it really makes you wonder, for everyone listening, think about it. With these kinds of fusions happening, what innovations could pop up in your own life, your own industry?
Right. Imagine fashion that adapts, healthcare that's seamless, truly sustainable tech.
The potential is just immense, isn't it? Really exciting times ahead exploring these intersections.